Hi, welcome to Algebra 1 with Miss Andrea. Today we're going to continue on in our unit about comparing and contrasting functions. And we're going to look at the different types of functions we've studied so far and look at their features and what things you should be able to use to identify exactly what you're looking at and see what kind of function it is. So this is going to be, it's in the online book as module 7, but it's labeled unit 5, I believe, and this is page 3. So we're calling this lesson 3. So comparing and contrasting functions, lesson 3. All right, so to jump right into it, we've got here some linear functions, some lines for us. Now, they don't always have to go in this direction. They could go in this direction or straight across like this, a horizontal line. So this is one with a negative slope. This is one with a positive slope. This one has no slope. And then the other is a vertical line. This is not a function. It does not meet the definition of a function. Okay. Now, any of these lines we will find in the slope-intercept form, usually that's how it's written mathematically. So y equals mx plus b, where m is the slope and b is the y-intercept. The average rate of change is constant. That means the slope is constant. And we know the slope is m equals something. So for example, this is m equals 0. This could be something like m equals 1. This could be something like m equals negative 2/3. So that brings us to the and no matter, it's constant, meaning no matter what point on the graph you're looking at, A to B, you're going to have the same slope as you have between A and D, between C and D, between B and D. They're all going to have the exact same slope on a line. And so anytime you have a constant slope, that is a linear function, okay? Now, to determine whether it's decreasing or increasing depends on the slope. If it's a negative slope like this one, you can see that the line is going to be decreasing. If it's a positive slope like this one, you can see that it's increasing. Anytime you have a slope of 0, it will be horizontal no matter what. That is the one outlier. It's either positive or negative for increasing or decreasing, and then the one outlier or anomaly of a horizontal line of 0. Remember, we're not considering a vertical line because that's not a function. Lines have no minimum and no maximum. So when we were studying parabolas, we saw the vertex was the minimum and the maximum. We do not have those in linear functions. There's no minimum and no maximum. Last thing I want to look at with these linear functions on this graph is domain and range. Remember, domain is all the possible x values. So with linear functions, they go all the way from negative infinity to positive infinity. And it's the exact same with the range. It goes all the way from negative infinity to positive infinity. There's any possibility of numbers. The one outlier or anomaly, again, is going to be the horizontal line with a slope of 0. The only thing that changes with this is going to be what? The domain or the range. That's right, it's going to be the range because this is going to have y equals, let's say, 3. That means that there's only 3. The range is only 3. There is nothing above it, nothing below it. So that's an anomaly. But standard is going to be domain is all real numbers and range is all real numbers. And remember to write that, you could write it like this, or you could write it like this. All real numbers, all real numbers. Now, you don't always see it in graph form. Sometimes you have the ordered pairs written out in a chart. So if you notice, there's an x and a y. In this case, our y is f of x because we're working with a function, but you could always call this the input and the output. And so when you have an input and output chart, the first thing you want to pay attention to is the inputs. You want to make sure that they are consistent. So the difference between -2 and -1 is 1. The difference between -1 and 0 is 1. 0 and 1 is 1. 1 and 2 is 1. And since all of those are 1, we can really focus only on our y's because remember, is change in y over change in x is how we determine our slopes or the differences. And so when you're dividing by, if the change in x is 1, if you're dividing by 1, then it doesn't matter what the change in y is. The change in x isn't going to change anything. So we can just look at the change in y and determine that. So if you remember from the last unit, we looked at this already and determined the difference between linear and quadratic just from looking at a chart. Do you remember what it was? Well, when you look at the change in the output, if the difference in the output is consistent or the same number every time, then you're going to have a linear function. So the difference between 17 and 13 is 4. The difference between 13 and 9 is 4. The difference between 9 and 5 is 4. And the difference between 5 and 1 is 4. That means the numbers 17, 13, 9, 5, and 1 are an arithmetic sequence because they have a consistent difference. But since our output values is an arithmetic sequence, the relationship between the input and the output is a linear function. So one of the ways you can tell if you have a linear function when you're looking at a chart is if the output values have a consistent difference, meaning they're an arithmetic sequence. Now, this linear function, is it increasing or decreasing? Well, as the input increases, the output is decreasing. So this is a decreasing linear function. All right, so now let's look at some quadratic functions. Remember, this should be very familiar to you because we just finished a unit on quadratics, but they look like parabolas, right? Or they look like a U-shaped or an arc. And the name of that is a parabola. This is a parabola that opens up. This is a parabola that opens down. Remember, the vertex is going to be, the vertex is going to be where it changes direction from going down to up or up to down. So the vertex is also going to be known as its minimum and its maximum. This is the minimum that this graph can reach, and this is the maximum y value that this graph can reach. Now, quadratics are usually written one of two ways, either in standard form, which is ax squared plus bx plus c, or the vertex form, which is a times x minus h squared plus k. And they told us different information, but as long as you can recognize that when you see something written to the power of 2, where you have the variable raised to the power of 2, or a second degree polynomial, then you know that you have a quadratic. Increasing and decreasing, you need to be able to identify that this is both decreasing and increasing, and the interval of increase is from h to infinity. The interval of decreasing is from negative infinity to h. And then that just flip-flops on this one. The interval of increasing is from negative infinity to h, and then the interval of decreasing is from h to infinity. Domain, the domain for all quadratic equations, no matter which one you have, is going to be all real numbers. And remember, this is the way to write that in set notation. So from negative infinity to positive infinity, all real numbers. And you see the domain is the same no matter which one you have. Range, our range is, again, our y values. And since we have a minimum and a maximum, there's going to be some stoppage points, some places where you can't go past, okay? And that's going to be our k in the vertex. Remember, our vertex is hk, k is the y value. So the k in the vertex in an opening upward parabola is going to be the first letter, and it's going to be a bracket because it is included in the range, and it goes all the way to positive infinity. The range for an opening downward parabola is from negative infinity to k. Remember, use that square bracket because we're including it. So do y'all remember how, when you have a chart, how to tell if it's quadratic? Well, for linear, we had to find the difference. Oh, that's a horrible line. Let's see if I can do that a little bit better. Not too much. But for quadratics, we had to find difference 2. If the second difference is consistent, then that's when we know it's quadratic. All right, so let's look at the difference between these. The difference between 4 and 1 is 3. The difference between 1 and 0 is 1. The difference between if I take 0 and subtract 1, I'm going to get -1. And if I take 1 and subtract 4, I'm going to get -3. Now, those aren't consistent. But if I take those differences, 3 minus 1, I get 2. 1 minus -1, I get 2. -1 minus -3, I get 2. So if you notice, my difference 2 is consistent, and therefore I have a quadratic function. Okay. My little cheat for this that says, oh, I need to pay attention, it's probably going to be quadratic, is you can clearly see the vertex in here because the y's are going down and then they go back up again. Okay, so you can see it's creating almost a parabola-like experience just with the numbers alone from going down and then back up. And that's my indicator. Hey, Andrea, pay attention. This is probably a quadratic. So if you see that, you can then make sure you check for the second difference. The last type of graph we're going to go over is the exponential functions. Now, there were two different kinds of exponential functions. There's exponential growth as well as exponential decay. So this is going to be, on my picture here is an exponential growth formula. And if you remember, an exponential function has the variable as the exponent, and the b has to be greater than 1 for it to be an exponential growth. If it's less than 1, it's going to be decay, right? Now, there's always there's going to be a y-intercept here in this one as well. This is 0, 1 in our standard exponential function. The domain and the range, well, what is the domain of this? Is there anything that it cannot be for x's? No, the domain is all real numbers. Domain is all real numbers, negative infinity to positive infinity. The range, is there anything that it cannot be with the range? Any y's? Do you remember with exponential functions, if there was a limit to our y's? Well, there is. There's going to be a horizontal asymptote. In this particular graph function, it's going to be 0 here. X equals 0 is the asymptote. Oh, look, it says horizontal asymptote right there. So x equals 0 is our horizontal asymptote, and that helps us determine our range. It can't go any further down below what our asymptote is. And so in this particular case, our range is going to be from 0 to infinity, because this graph is always approaching 0, getting closer and closer and closer, but never actually touching it. So it's not going to be included. Now, whatever your asymptote is what's going to go in this place. It's not always going to be 0. It's going to be whatever the asymptote is, but the domain is always going to be all real numbers. Okay, ranges from the asymptote to infinity. Now, is this increasing or decreasing? Well, this is growth, so this is going to be increasing. Minimum and maximum, there is no minimum, there is no maximum. All right, here's another one, and this one is exponential decay. And so you can see that this has the exact same formula as before, where we have x as the exponent, but in this case, b is going to be greater than 0, but less than 1. Remember, it has to be greater than 0 because what happens if it's less than 0? It reflects across the x-axis. So in this particular case, for exponential growth, it's going to be greater than 0, but less than 1. And remember, this is for a decay function. So this also has a y-intercept. The domain is exactly the same. The range is exactly the same from the horizontal asymptote to infinity. This one is decreasing, right? There is a horizontal asymptote. In this particular case, it's x equals 0 again, and there's still no minimum or maximum. So what does this look like on a chart? We talked about linear and quadratic chart functions and how to identify them on the chart, but how do you identify it for an exponential graph? Well, the easiest way to look at it is it being multiplied or divided consistently? Well, 1/4 times 1/2 I'm sorry, 1/4 to 1/2 to 1 to 2 to 4. Let's see if we can find a difference. Let's start there to see if how it looks difference-wise. Well, 1/4 to 1/2, the difference of there is 1/4. 1/2 to 1, the difference is 1/2. 1 to 2, the difference is going to be 1, and 2 to 4, the difference is 2. Well, that's definitely not linear. Let's look at difference 2. 1/4 to 1/2 is going to be 1/4 again. 1/2 to 1 is 1/2, and 1 to 2 is 1. Difference 2, that's not consistent. It looks like they just moved down 1, didn't they? Well, difference 2, that means it's not quadratic. So with those two out of the way, I can begin to look at this possibly as a geometric sequence. That means that if our y values are increasing in a manner that's by a ratio or a proportion, so by multiplying or dividing by the same number. So I'm just going to look at this going downwards. 4 to 2, what did you do? You divided by 2, right? Half of 4 is 2. Half of 2 is 1. Half of 1 is 1/2. And half of a half is 1/4. So the y values are a geometric sequence, which means the relationship between the input and the output is going to be an exponential function. All right, because they're being multiplied by a factor of 2 going up or divided by 2 going down. Well, I said that backwards. Multiplied by 2 going down or divided by 2 going up. All right, so that's an exponential function. Is it growth or decay? Well, as x is increasing, what's happening to our y or our output? It is increasing as well. So this is an exponential growth function. All right, so now we need to look at some real world situations and determine what type of graph or modeling are we going to have. In a bowl of M&Ms, we have 6,000 candies, and every hour Joe comes by and he takes half of what's in the bowl, right? So the first time he takes 3,000. Then after that, he's going to take 1,500. He always takes half because he never wants to leave the bowl empty. He doesn't take the whole thing. So if it's decreasing by half every time, we know that that's going to be a proportion or a ratio. And so this is going to be exponential decay because it's getting smaller every time. Miss Andrea starts with 325 pencils on the first day of her school. Each week, her supply decreases by 12 pencils. Okay, and I should have done this on the last one, but the easiest way to do this is to look at a chart, the input, the output. Day 1, 325 pencils. Day 2, decreases by 12 pencils. 325 minus 12 is 313. Day 3 is going to be 301. Day 4 is 289, etc. And if you notice, the difference between those every time is 12. And that's a difference 1, which means this has got to be an arithmetic sequence in the y's. So the relationship that's being talked about, the input, the days, and the output is going to be a linear function. And is it increasing or decreasing? It's decreasing. So it's a decreasing linear function. All right, a plumber charges $150 an hour minimum plus $15 per hour. All right, let's create a chart. The input and the output. Hour 0, you're going to be charged $150 if the plumber is not there for even 1 hour. After 1 hour, he's going to be charged what? $150 plus 15, which is $165, plus 15 is $180 for hour 2. Hour 3, it's going to be $195. All right, so the difference between each of these is what? It's 15. So that's an arithmetic sequence. Since there's an arithmetic sequence in the outputs, that means we're going to have a linear function. Okay, is it increasing or decreasing? Well, the y value, as the x values are going up, the y values are going up. So it's an increasing linear function. There you go. A golfer hits a ball into the air. I'm going to stop right there and just say we already know projectiles are what? They're parabolas, which means I bet you this one's going to be quadratic. But let's look at it. A golfer hits the ball into the air. The height of the ball is measured over the next several seconds. After 2 seconds, the ball reaches its maximum height of 115 feet. So second 0, second 1. I don't even need to do a chart for this one because they don't give me enough information. I just know based on what's being described, time, distance, or time and height rather, and the ball is a projectile, I know that that's going to be quadratic. Each year, Josie counts the number of ants in her ant farm. The first year, she counted 15 ants. She notices that the ants double every year. So year 1 is 15, input, output. Year 2 is going to be 30. Year 3 is going to be 60. Year 4 is 120. Wow, she needs to get rid of some of those ants. All right, so if it's increasing by doubling every year, which one of these is it? It's going to be exponential growth. Let's see, is that it? I think that's the last one. Now, if you notice, we didn't do any arithmetic sequence or geometric sequence in this one. Arithmetic sequence or geometric sequence are going to be when you have a series of numbers that doesn't have a relationship, like every month, every year, every something where there's a relationship between an input and an output. If it's just a series of numbers, it's going to be a sequence. Okay, but if there's a relationship between it, then that sequence that you'd see in the output values, the relationship with the input values, that would be a function. So that's how you would get to both of those. All right, well, that's it.